Dear students, now let us discuss the new chapter. That's the third chapter of our first unit. It is congruences. What is congruence? Congruence means for any two integers a and b are any two integers with m is a positive, m greater than 0, then a congruence to b mod m. A congruence to b mod m means m divides a minus b. M divides a minus b, or m congruence to b mod m means a minus b congruence to 0 mod m. A minus b congruence to 0 mod m. So this is the definition of congruence. Means m divides the difference of a and b. Here m is called the modulus of the congruence. M, what is m? The positive real m called the modulus of the congruence. Modulus of congruence. So a congruence to b mod m, that means m divides a minus b. Then a congruence to 0 mod m. A congruence to 0 mod m means it is m divides a. Or reversely, if m divides a, that means m divides a minus 0. That means a minus 0 is congruence to 0 mod m, or a congruence to 0 mod m. So means a congruence to 0 mod m if and only if m divides a. Agreed. Now a congruence to b mod m if and only if a minus b. Similarly, a congruence to b mod m. A congruence to b mod m if and only if m divides a minus b. Okay. A congruence to b mod m means m divides a minus b. Reversely, when m divides a minus b, what happens? When m divides a minus b, that means m divides a minus b minus 0. M divides a minus b minus 0, that means a minus b congruence to 0 mod m. That means a congruence to b mod m. So if m divides a minus b, a congruence to b mod m if and only if m divides a minus b. A congruence to 0 mod m if and only if m divides a. If m does not divide a minus b, if m does not divide a minus b, that means a minus b is incongruence to 0 mod b, or a minus b is incongruence to 0 mod m. That means a is incongruence to b mod m. M does not divide a minus b, that means a minus b is incongruence to 0 mod m, that is a is not congruence to b mod m. Okay. Now, by this definition, suppose n is even, what happens? When n is even, then n always congruence to 0 mod 2. If n is even, then n congruence to 0 mod 2. Okay. If n is even, then n congruence to 0 mod 2. Why? N is even means, what is even? N is even means n equals some 2k. Okay. Where k is any integer. N is 2k where k is any integer. That means 2 divides n. N is even means 2 divides n. 2 divides n means 2 divides n minus 0. That implies n minus 0 is congruence to 0 mod 2, means n is congruence to 0 mod 2. So if n is even, then n congruence to 0 mod 2. So n is even if and only if n is congruence to 0 mod 2. This implies and is implied by. Why? When n is congruence to 0 mod 2, clearly 2 divides n minus 0, clearly 2 divides n, thus n is congruence to 0 mod 2. So if n is even, then if and only if n congruence to 0 mod 2. N is even, if and only if n congruence to 0 mod 2. First, suppose that n is even, then it means 2 divides n, implies 2 divides n minus 0, that implies n congruence to 0 mod 2. Reversely, When n complements to 0 mod 2, that means 2 divides n minus 0, that means 2 divides n, 2 divides n means n equals to k, hence n is even. Suppose n is odd, what happens? N is odd. When n is odd, then n complements to or n minus 1 or n complements to 1 mod 2. When n is odd, then n complements to 1 mod 2. How to prove? If and only if condition. Again, if and only if n is odd, if and only if n complements to 1 mod 2. How? Suppose n is odd. N is odd means if n is, first suppose that n is odd. N odd. N odd means n minus 1 is even. N minus 1 is even. Then n minus 1 is even means when n is even, n complements to 0 mod 2. So n minus 1 is even means n minus 1 is complements to 0 mod 2. That implies n complements to 1 mod 2. Okay. N minus 1 is complements to 0 mod 2. That implies n complements to 1 mod 2. N minus 1 complements to 0 mod 2 means it is 2 divides n minus 1 and so on. Now reversely, suppose n complements to 1 mod 2. When n complements to 1 mod 2, n minus 1 complements to 0 mod 2, that means n minus 1 is even. N minus 1 is even means n is odd. So we have if n is even, then n complements to 0 mod 2, and if n is odd, then n is complements to 1 mod 2. Agreed. All of these things are done by using the definition of the congruences. If A complements to, then or for all A complements to B mod 1, this is true for every A and B. A complements to B mod 1 for all A, this is true for every A and B. A complements to B mod 1 for every A and B. How? That's immediate. Why? Because 1 divides A minus B. A minus B is a multiple of 1. 1 divides A minus B means A minus B is a multiple of 1. That means 1 divides A minus B implies A minus B complements to 0 mod 1. A minus B complements to 0 mod 1. A minus B complements to 0 mod 1 means A complements to B mod 1. So for every A and B, A complements to B mod 1. Agreed. Now, if A complements to B mod M, if A complements to B mod M, then A complements to D, then A complements to B mod D. If A complements to B mod M, then A complements to B mod D if whenever D divides M. D divides M, comma D is positive. A complements to B mod M. If A complements to B mod M, then A complements to B mod D if D divides M for D greater than 0. How? For A complements to B mod M. A complements to B mod M means it is M divides M minus B. A complements to B mod M means M divides M minus B. But D divides M. M divides M minus B. D divides M. That means D divides M minus B. Agreed? M divides M minus B, but D divides M, then D divides M minus B. D divides M minus B means M minus B is complements to 0 mod D. M minus B is complements to 0 mod D. That means A complements to B mod D. A complements to B mod D. So, that's the next result. If A complements to 0 mod M, then A complements to 0 mod D only if D divides M. By D divides M divides M minus B, and D divides M means D divides M minus B. So, hence, according to the definition, hence by the definition of congruence, immediately A complements to B mod D when D is positive. And the congruence is always an equivalence relation. Congruence is an equivalence relation, so that's immediate. And it is left as an exercise for you. Now, consider if A congruence to B mod M, next we consider another result. If A congruence to B mod M, if A congruence to B mod M, and alpha congruence to beta mod M, if A congruence to B mod M and alpha congruence to beta mod M, then the first result is ax plus alpha y congruence to bx plus beta y mod M. Ax plus alpha y congruence to bx plus beta y mod M. How? Similarly, why? A congruence to B mod M. A congruence to B mod M means M divides, it is given, M divides A minus B. Okay. Also alpha congruence to B mod M means M divides alpha minus beta. So M divides A minus B and M divides alpha minus beta. That means M divides X into A minus B. If M divides A, M divides AB. And M divides alpha minus beta means M divides Y into alpha minus beta. Okay. So it is, that means M divides X into A minus B plus Y into alpha minus beta. That means M divides AX minus BX plus alpha by minus beta y. That is M divides AX plus alpha y minus of BX plus beta y. M divides AX plus alpha y minus of BX plus beta y. That means AX plus alpha y is congruence to BX plus beta y mod M. Okay. BX plus beta y mod M. AX plus alpha y congruence to BX plus beta y mod M. Agreed. So this is the first result. If A congruence to B mod M, alpha congruence to beta mod M, then X plus alpha y congruence to Bx plus beta y mod M. Now, when A congruence to B mod M and alpha congruence to beta mod M, then A alpha congruence to, then the next result is, then A alpha congruence to B beta mod M. Then A alpha congruence to B beta mod M. How? When A congruence to B mod M, alpha congruence to beta mod M, then A alpha congruence to B beta mod M. That's immediate. By this again given M divides A minus B and M divides alpha minus beta. Okay. So A alpha congruence to B beta mod M. How this one? M divides A minus B and M divides alpha minus beta. That means M divides A minus B, M divides A minus B means M divides alpha into A minus B. Okay. Plus, sorry, and M divides B into alpha minus beta. Clear? M divides A minus B, that should imply M divides alpha into A minus B. M divides alpha minus beta, then M divides a constant into a scalar into alpha minus beta. That means it is M divides alpha into A minus B plus B into alpha minus beta. That means M divides alpha A minus alpha B plus alpha B and minus B beta. That is alpha A minus B beta. M divides alpha A minus B beta means alpha A congruence to B beta mod M. Okay, way to finish. So if A congruence to B mod M and alpha congruence to beta mod M, then A alpha congruence to B beta mod M. So this is the second result. Again, if A congruence to B mod M, and alpha congruence to beta mod M, then a power n congruence, if a congruence to b mod m, then a power n congruence to b power n mod m. If a congruence to b mod m, then a power n congruence to b power n mod m for all positive integers n. For all positive integers. This can be proved by using induction hypothesis. How? So, when m divides a minus b, this given a congruence to b mod m. That means m divides a minus b. Okay. What is when m divides, we also prove that when m divides a minus b or a congruence to b mod m and alpha congruence to beta mod m, we already proved that a alpha congruence to previous result, a alpha congruence to b beta mod m. Okay, a alpha congruence to b beta mod m. So, a alpha congruence to b beta mod m. This is already proved. Enough. So, when m divides a minus b, put a alpha congruence to b beta mod m means from here it is m divides a alpha minus b beta. Agreed. So put a alpha equals a and beta equals b. In this result, what you get? It is m divides a square minus b square. M divides a square minus b square means a square congruence to b square mod m. So the result is true for n equals 2. Agreed. By using the just above argument, we have m divides a minus b. Then we already proved that a alpha congruence to b beta mod m. That means m divides a alpha minus b beta. You can replace alpha by a and beta by b. Then m divides a square minus b square. That means a square congruence to b square mod m. Okay. So the result is true for n equals 2. Agreed. Now you see the result is true for n minus 1. What do you get? A power n minus 1 congruence to b power n minus 1 mod m. A power n minus 1 congruence to b power n minus 1 mod m. Also we have m divides a minus b. Okay, m divides a minus b. A power n minus 1 congruence to b power n minus 1 mod m means here m divides a power n minus 1 minus b power n minus 1. Therefore, m divides a into a power n minus 1 minus b into b power n minus 1. That means m divides a power n minus b power n means a power n congruence to b power n mod m. So the result is true for n. So by induction hypothesis, when a congruence to b mod m, then for every positive integer n, a power n congruence to b power mod m. This is the another result. Agreed? Okay. Now, using this argument, a congruence to b mod m and alpha congruence to beta mod m, if a congruence to b mod m, if a congruence to b mod m and alpha congruence to beta mod m, then for any polynomial f, with an integer coefficient, f of a congruence to f of b mod m. If a congruence to b mod m, then for any polynomial f with an integer coefficient, f of a congruence to f of b mod m. How? So first, suppose f is a constant polynomial. That means degree of f equals 0. When degree of f equals 0? Degree of f equals 0 means consider the polynomial f of x equals some lambda or a constant. F of x equals a or lambda, whatever. Or f of x equals a naught. In generally, we take it as f of x equals a naught. F of x is a polynomial with an integer coefficient, then f of x equals a naught. F of x equals a naught. So what is f of e? F of a equals a naught and f of b equals also a naught. F of a equals a naught, f of b equals a naught. But what about a0 minus a0? a0 minus a0 means 0. Agreed. So, and m divides 0 means m divides a0 minus a0. That means m divides what is 1 a0, that is f of a, and then the second one is f of b. So from here m divides f of a minus f of b means f of a congruence to f of b mod m. Okay. So when degree of f is 0 means f is a constant polynomial. Then when a congruence to b mod m, we have f of a congruence to f of b mod m. Okay. Now, suppose degree of f equals 1. What happens? Degree of f equals 1. So degree of f equals 1 means, what about f of x? What about f of x? F of x equals a0 plus a1x. Okay. So what about f of a? F of a equals a0 plus a1a. And what about f of b? F of b equals a0 plus a1b. Okay. Now, m divides it is given m divides a0 minus a0 means m divides 0. Also it is given a is congruence to b mod m means m divides a minus b. So m divides a minus b means m divides a1 into a minus b. Sure. Yes. M divides a1 into a minus b. Therefore, we have m divides a0 minus a0 means m divides a0 minus a0 plus m divides a minus b means m divides a1 minus b. So consider these two. M divides a0 minus a0 and m divides a1 into a minus b. So combinedly we have m divides a0 minus a0 plus it is a1a minus a1b. Okay. That means m divides a1a plus a0 or a0 plus a1a, a0 plus a1a minus a0 plus a1a minus of a0 plus a1b. Agree. What is a0 plus a1a? That is f of a. That means m divides f of a minus what about this one? That is f of b. So m divides f of a minus f of b means f of a congruence to f of b mod m. So when degree of f is 1, the result is also finished. Okay. Now assume. Now to prove the result is called for any polynomial of f degree n minus 1. Using induction hypothesis, you can prove the result is true for n. That is in the next class.